There are many situations where we are dependent on stored electrical energy. We could hardly imagine living anymore without batteries and a constant source of electricity. Whether in our cell phones, our laptops, or in electrically powered bicycles, batteries are increasingly a feature of everyday life. Electrically powered vehicles are increasingly important in urban transport, and they need high-performance batteries. We can trace the development of batteries back to a man who was the first to find a source of energy that produced a constant electric current, and so ushered in the age of electricity. Alexandre Volta was born into an aristocratic family in the Italian town of Como on the 18th of February 1745. Even as a schoolboy, he showed a great interest in science, in particular electricity. At this time, while the phenomenon of electricity as such was familiar, not much was known about its origins. Itinerant showmen would demonstrate the strange effects of electric current to crowds that looked on in amazement. Mysterious crackles, bright sparks, and, the climax of the performance, a dagger point that could ignite alcohol. In 1769, still only a 24-year-old student, Alexandre Volta published a scientific article with the Latin title De Via Tractiva Ignis Electrici, on the attractive force of electric fire. 6 years later, he was appointed to teach physics in his hometown of Como, but to start with, he also concerned himself with chemistry. In the early years of his time in Como, he developed the electrophorus, a device that generated electricity by friction. An electrophorus consists of two parts, a metal stamp with an insulated handle and a cake of resin. When the resin is rubbed with cat's fur, electricity is produced by friction. This electricity is transferred to the metal stamp, which discharges in a moment. By rubbing it with the cat's fur, excess negative charges are created in the resin cake. If the electrically neutral metal stamp is held close to the plate, the positive charges in the stamp are attracted by the negative ones in the cake. They collect on the side of the stamp facing the cake. The negative charges in the stamp are, by contrast, repelled and collect on the upper side. If this side is grounded, the negative charges are drained away. This means that the metal stamp is now deficient in negative charges. If it is removed from the cake, it is positively charged. If, however, a grounded rod is brought close to the plate, there is a flow of electric current. A spark flies, restoring the balance of charges. This disparity in charge is known as a potential difference, and the more the cake and the metal stamp are separated, the higher it is. The easiest way to imagine potential difference is by analogy with a water pipe. Here, the potential difference corresponds to the pressure of the water in the pipe. The pressure may be high even if no water is flowing. This is the case when the tap is turned off. The same is true of potential difference. It may be high even if there is no electricity flowing, no current, in other words. With his electrophorus, Volta succeeded in producing an inexpensive device that could generate high potential differences. His research led to his appointment at the age of 35 as professor of physics at the University of Pavia. But Alessandro Volta wasn't the only one to be taking an interest in electricity. In 1789, the professor of anatomy in Bologna, Luigi Galvani, started experiments with frogs' legs. He made a surprising observation. If he touched the nerve fibers of amputated legs with two different metals, the muscles would suddenly twitch. Galvani was convinced he had proved the existence of animal electricity. When Volta heard about Galvani's results, he was fascinated. At once he set out repeating the experiments. However, he did not believe in Galvani's explanation. By performing his own experiments, he discovered that the reason for the electric current lay not in the muscles and nerves of the prepared frog's leg, but in the two different metals. The fluids in the tissues of the frog merely acted as a conductor. Volta showed that as long as you have a conductive liquid such as brine, all you needed was two different metals in order to demonstrate an electric effect. This is known as the voltaic effect. He started experimenting with various metals and looking into their properties. His measuring instrument was his own tongue. If you touch it with two different metals at the same time, an electric current will flow. It makes itself felt as a tingly, sour taste. Painstakingly, Volta tested every possible combination of metals. He entered them in a table. The order corresponded to the strength of the electric reaction. However, he didn't only investigate metals like zinc, tin, lead, iron, copper, platinum, gold, silver, and mercury, which he called conductors of the first class. He also discovered that liquids and bodily fluids were conductors too. These he called conductors of the second class. His results meant that his long-lasting dispute with Galvani was finally settled in his favor, and the upshot was an invention that made him world famous. For in his experiments, he had realized that the electrical effect could be substantially increased by introducing an acid between the different metals. He constructed a device which made him famous, the voltaic pile. Volta constructed a column consisting of copper coins alternating with plates of zinc. The metals were separated by leather discs soaked in brine. When he connected the two ends of the voltaic pile with a wire and his hand, electric current flowed. Volta had invented the first battery. But how does it work? What's going on inside the voltaic pile? A battery converts chemical energy into electrical energy. There are two chambers separated by a porous membrane. In one chamber is a zinc electrode, in the other a copper electrode. The function of a battery is based on the different chemical reactions of the metals. The zinc electrode gives off positive ions to the solution. The resulting deficiency means it is now negatively charged. Something similar happens in the copper cell, but on a much smaller scale. This is because copper has a much smaller tendency to give off positive ions than zinc. We say that it is less oxidative. This also means that the negative charge is much less than on the zinc electrode. If the electrodes are now connected by a metal wire, the surplus negative charges, or electrons, now flow along the wire from the zinc electrode to the copper electrode. This does not last long though, because sooner or later the chemical processes in the battery stop. Even so, the voltaic pile was the first device which created an electric current for any length of time. It was a crucial step in the further investigation of electricity. After almost 10 years of tireless research, Alexandre Volta finally reached his goal. At the age of 55, he announced his new invention in a letter to the Royal Society in London. The renowned British Scientific Academy honoured Volta with its highest award, the Copley Medal, in the days before Nobel Prizes, probably the pinnacle of scientific achievement. The following year, 1810, Volta went to Paris, where he demonstrated his voltaic pile to the French Academy of Sciences in the presence of Napoleon. The emperor was much taken by the invention. He granted Volta an annuity, naming him a count and a senator of Italy, which was then under French occupation. In 1815, Volta became director of the philosophical faculty in Pavia. 4 years later, he retired to Como, where he died on the 5th of March 1827, at the age of 82. More than 50 years later, from August to November 1881, the Palais de l'Industrie in Paris played host to the first International Electrical Congress. Numerous technical innovations were presented, such as Siemens' electric tram and Edison's electric lighting system using incandescent bulbs. But the main purpose of the participants was to standardize electrical units. Volta was honored by having a physical unit named after him. The International Electrical Congress chose the name volt for the unit of electric potential difference, or electromotive force, and it is still valid today. Count Alessandro Volta was seen in the 19th century as the founder of a new age, the age of electricity. Today, there are all sorts of different batteries, but one thing has not changed since Volta's day. Sooner or later, they're exhausted. They run flat, and no more current is produced. They then have to be exchanged. As in Volta's day, most batteries use two different metals, but these metals and the acids that batteries also contain are not environmentally friendly, especially when the batteries are not properly disposed of. That's why the search is on for new combinations. Investigations are going on into high-performance batteries that use natural organic compounds, which are biodegradable after use. For years, science and industry have been working on the development of new batteries with a higher energy density and which are absolutely leak-proof. In place of metal containers, plastic foil coated in aluminium or some other metal is being tried. This allows the battery to have any shape you want. Very useful when you have to integrate the battery into a designer product like a mobile phone or laptop. But performance has not been forgotten either. Large batteries, for bicycles for example, are also being developed. A mobile electricity supply has a high priority in our modern society. Although the development of batteries is proceeding apace, the principle is the same as it was in the original voltaic pile.